In this video, we're going to work example problems related to symmetry and transformations. So let's get started. Which of these letters have symmetry with respect to a line? So let's start with M, capital M. Okay, so we know that for a figure to be symmetric with respect to a line, every single point on the figure needs to have a corresponding point on the opposite side of the line. This is really the definition of symmetry in regards to symmetry about a line, a plane, or a point. So it's really more about what is the meaning of a corresponding point. So, all right, well, it looks like this is going to have symmetry about a vertical line right down the center. And the reason is because we can take any point on this letter, and it's going to have a corresponding point on the other side of the line. So corresponding means, for the case of linear symmetry, so if we start with this point here, and then from this point we draw a line that's perpendicular to the line of symmetry and also is bisected by the line of symmetry. So it's perpendicular and it's bisected. We end up, where we end is on the figure. If we can find one point on the figure that doesn't have a corresponding point in this sense, then it's not symmetric with respect to that line. But here we can see that any point we pick, we can find a corresponding point on the other side. Perpendicular, and it's bisected. Okay, but that looks to be the only line of symmetry here. Because, for example, if we maybe did a line like a horizontal line right down the center, well, we can automatically see that, all we need to do is find one point that doesn't have a corresponding point. Well, let's do this point. Okay, draw a line from this point perpendicular to the main line and also bisected. Well, look, we're not on the figure, so there you go. That's not a line of symmetry. So just the vertical line right down the center looks to be the only line of symmetry here for the letter N. Okay, let's do the letter N. Okay, so we can start with maybe a vertical line like that. Well, okay, well, actually, no, that's not going to work, because let's pick this point here, draw the perpendicular bisector. No, we're not back on the figure, so no. Okay, same idea with a horizontal line. Do this. No. Okay, maybe a line like this. Right? So, okay. Well, it looks like it would work here, right at the ends. Right? That's perpendicular, bisected, but like this doesn't count, because it's not perpendicular to the line of symmetry. So, okay, it works there, but let's see. It works going across. Let's see. What about, yeah, but no, it's not going to work, because no. What about let's see. What about a line like this? Well, no, that's not going to work either. So no lines of symmetry here. Okay, what about the letter P? No. I mean, you could just intuitively see there's no way, based on what we just did with the letter N. I mean, the letter N looked like it was pretty symmetrical, like it was going to have at least one line of symmetry. And so here, no way. Because no matter where you draw the line, you can just think about it. No matter where you draw the line, if we drew the line, right here, but okay, what about these points down here? Right, so no. Okay, what about T, capital T? Well, okay, right down the middle. Yep. So, I mean, every line is one dimensional, so there's no, we don't think like, okay, well, we're symmetric about the line. No, we're over these two lines right down the middle, the leg of the T here and the blue line are like right on top of each other. They're both one-dimensional. So a line has no width, right? So all we're looking at is just here. Well, yeah, every point here is going to have a corresponding point. So yes, the T has a symmetry with respect to that vertical line. What about another line of symmetry maybe? So maybe like that, but no, because you'll, right? I mean, there's no way. These might have point symmetry, which we'll look at in a second. Okay, what about the letter X? Okay, so what about this vertical line here? Okay, that checks out there. That checks out there. Yeah, there we go. All of these are perpendicular bisectors, so every point's going to have a corresponding point. Okay, but it looks like this is going to have more than one line of symmetry as well, because we've got, right? These are all perpendicular bisectors. Okay. Okay, now same question, but we want to see if the letters have symmetry with respect to a point. Now, note that as we talked about in going through the textbook, we just saw like X has two lines of symmetry. So a figure can have more than one line of symmetry, but it can only have one point of symmetry. A figure can have no points of symmetry or one point of symmetry, or it could have no lines of symmetry or multiple lines of symmetry. So, okay, let's start with M. Okay, now, okay, what is point symmetry? What is the symmetry of a figure with respect to a point? What does that mean? Well, okay, again, all of these symmetries with respect to points, lines, planes have the same fundamental definition in that every single point on the figure is going to have a corresponding point on the figure with respect to that line or that point or that plane. So it really comes down to, well, what does a corresponding point mean with respect to a line or a point or a plane? Well, we just looked at what a corresponding point meant with respect to a line. With a point, it's just going to be that there's no perpendicularity involved. It's just that the point bisects the two corresponding points. So you take 2 points on the figure, you connect them with a line that goes through the potential point of symmetry, and that point of symmetry needs to bisect that line. And then those are 2 corresponding points. So with that, then you have to have every single point on the figure have a corresponding point on the figure with respect to that point of symmetry. Then it's a point of symmetry. So okay, but with that, then with that definition, what you can see is that any point of symmetry is going to need to be kind of in the middle of all of the points on the figure, right? Like, so we know then the point of symmetry is going to need to be somewhere around here. Has to be. You might say, well, why couldn't it be down here? Well, because then how are we going to, okay, if we had a point of symmetry here, if we said it was here, that doesn't make any sense because, okay, we just pick a point on the figure, and now it needs to have a corresponding point somewhere on the figure with respect to this point of symmetry. Well, there's no way. How are we going to, okay, we drew a line to that point, now we need to draw that same length line to another point on the figure? There's no way, right? It has to be in the middle somewhere, like around here. Has to be. Okay, so like these 2 points are corresponding. All right, but again, when it comes to point symmetry, we're not limited by perpendicularity. So that's nice. So we could, we could do this. Those points are corresponding. Okay, but we can automatically see though that there's no way this is going to have a point of symmetry. Because look, all we need to do is just pick a point and then just draw a line through the point of symmetry, okay, or draw it to the point of symmetry. Now go twice that distance we just went, right? That's all you need to do to test. Pick a point, draw a line from that point to the point of symmetry, then go that same distance through. Well, we're not in the figure, so no. But we don't need to go testing other points if if we're in that middle region and we see a glaring no way to a point having a corresponding point, then we know it doesn't have a point of symmetry. Okay, let's do in. Okay, so we know it's gonna have, if it's gonna have a point of symmetry, it has to be somewhere in this middle region. It has to be. So let's put the point here. Okay, now let's see. Corresponding point, that's right. Those are corresponding points. Equidistant on both sides. Those are corresponding points. Equidistant on both sides. Yes, yes. We could do like this. Those are corresponding points. So yes, the letter N does have a point of symmetry. Okay, what about the letter P? Well, no. I mean, we're gonna have to be in like this central region here, somewhere around there. I mean, there's no way. There's no way. I mean, you can, right? No way. Okay, what about T? All right, maybe it's gonna have to be around there. Okay. Well, no. There's no way. Equidistant on both sides of the point of symmetry, but we're not in the figure. Okay. Let's see. So it would have to be here, right in the middle. And yeah, definitely. So this is the letter X is very symmetric. Point symmetry, 2 lines of symmetry. It actually has more than just 2 lines of symmetry. It has, right, this would be a line of symmetry. This would be a line of symmetry. You have a vertical line of symmetry, horizontal line of symmetry, and a point of symmetry. Okay, which geometric figures have symmetry with respect to at least one line? Okay, well, this definitely, I mean, I can see at least 2 lines, but probably even 4 lines with the diagonals. Okay, let's see. Here, it looks like there's not going to be any. Where could we draw? I mean, maybe like that. Maybe. But then, okay, perpendicular bisector. I mean, no. Okay, so maybe we make that this line the equidistant from like that. So perpendicular bisector there. Okay, there we go. That has a corresponding point, but let's see. Okay, maybe that does. Okay. Yeah, but no, because look. So no, I would say no here. Okay, let's see. This looks to have a vertical line of symmetry for sure, and a horizontal line of symmetry, and maybe more. Okay, same question. So, okay, just looking at this middle one here. Yes, in the vertical direction. No here, because you can see, right? Maybe the diagonals. So, yeah, there we go. No, but no here. No. So it looks like just the vertical, but maybe more. Here, no. Here, I would say no, but maybe straight across. So, yeah. Okay, yeah, straight across. And then maybe even, no, not straight down here, because it's not symmetric, right? You have an issue like here. So, but yeah, it looks like it has at least one. Okay, what about point symmetry here? So, okay, you think in the middle, but let's check. So, yeah, yes, yeah, there's symmetry there. Here, it looks like it's going to be yes as well here. So, yeah, definitely. Okay, now here, this should be no, because you can see, yeah, this has a regular pentagon has like 5 lines of symmetry, but you see, like you just see there that's not, those lengths aren't equal. Those lengths are, but yeah, I mean, we just saw, you can clearly see these lengths aren't equal. We could find another one somewhere. Let's do this. Huh. Maybe it's not as easy to figure out, but yeah, it's not. It's not. Yeah, it's hard to tell, but I think this is the best example right here. You can, those are not equal length. Okay, so I mean, all of these we can just start by putting the potential point right in the middle area. Okay, and let's start with the easier one here. This looks like a yes. Yes, this is going to be a yes. This looks like, I don't know. So maybe we want let's put the point at the diagonals. So yeah, but then that's not going to. We can clearly see that's not going to be a point of symmetry. And if it doesn't work on the diagonals, then it's not going to then it's not going to work. Then it's not symmetric. So yeah, but we can see it didn't even work on the diagonals. It's not going to work here, so no. Now here, yeah, I mean, this is a no. I mean, yeah, there's no way. Okay. Okay, which words have a vertical line of symmetry? So, okay, a vertical line of symmetry is going to have to be at the middle. There's no way. How could you have a vertical line of symmetry over here? So it's going to have to be at the middle. And let's see. So, okay, that works. That works. That works. It looks like a yes. Yes. Okay, let's see. Right down the middle there. Okay. Yep. Yep. This looks like a yes as well. Every point's going to have a corresponding point on the other side of that vertical line. Okay. Let's see. We've got yes, 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 yes. Yeah, yeah. That has a vertical line of symmetry. Okay. So, yes, yes, no. So, no, this does not. The word I, all capitalized, no. Complete each figure so that it has symmetry with respect to line L. Well, okay, we know if we want something to be symmetric with respect to a line, then we can reflect it across that line. So all we need to do is reflect this across the line. And we can get a sense for what's going to happen here. And that's, so like this point's going to have a corresponding point across. Every point's going to have a corresponding point on the other side of the line. And same exact idea here. So we can get a copy here. Now flip this horizontally. And there we go. So same thing here. And there we go. See? That has that vertical line of symmetry. Okay, same thing here. But we're going to do this. We're going to flip this with respect to a horizontal line. So we're going to flip this. We did the previous problems we flipped horizontally. Now we're going to flip these vertically, or flip them about a horizontal line. So okay, there we go. Now it's got this symmetry about the line M, right? There's corresponding points. Every single point on the figure has a corresponding point on the other side. Okay, same thing here. So there we go, like that. Okay, complete each figure so that it reflects across line L. So this is a little bit different because we don't have a horizontal or vertical line. And additionally, in this case, we've got this figure is offset a bit from the line. Okay, but the idea is going to be that when we mirror this, this is going to have a corresponding point based on the perpendicular bisector, right? So is this. So you could that could show you where this is going to go. Point A is going to go, draw the perpendicular bisector like that. So we can actually do this without having to copy and paste it, since we're dealing with triangles, which are relatively simple to draw. We can actually do this manually. So that looks about right. That's a perpendicular bisector. Okay, but then where are points B and C going to go? Well, they're not going to go anywhere, right? So all we need to do then is just do this. You see? There you go. Now we can do a similar process here, because we can say, okay, we've got these polygons are relatively easy to draw, like not like the butterfly and whatnot. So, okay, let me try and get this more accurate. Perpendicular bisector. Okay, perpendicular bisector to the line L. About right there. About like that. So with that we can do and there you go. Now we can just get rid of these reference lines. And there we go. Okay, same process here. Let's start with this one on the right. This looks easier. So, because H and L aren't going to move, they're on the line. Okay, so now we've got connect these. There we go. Okay, now here, what we can do is let's reflect those 2 points. Now let me try and put a, okay. And now about like that. Okay. And so then from there, we will just be, let's see. So connecting these points like this, then, and these points like that. See? Okay, suppose that triangle ABC slides to the right to the position of triangle DEF. Okay, so triangle ABC undergoes a slide or a translation straight to the right, and the resulting triangle is transformed into triangle DEF. Okay, if the measure of angle A is 63 degrees, find the measure of angle D. Well, okay, we know with any of these rigid body transformations, which includes the translations, the reflections, the rotations, everything we've studied in this section, we know that they're called rigid body transformations because they don't change the shape or the size of the figure, which means that the resulting figures are going to be congruent. So the answer to part C is yes. Yes, and so since they're congruent, all the side lengths are the same, all the angles are the same, at least the corresponding ones. So yeah, the corresponding ones. So it's tempting to look at this and say, oh, well, yes, 100%. Well, no, let's make sure they're not trying to trick us, and that they specified two non-corresponding side lengths. So we can see that AC corresponds to DF, CB corresponds to FE, AB corresponds to DE. So AC and DF are corresponding, so yes. Okay, if the measure of angle A is 63 degrees, what's the measure of angle D? Well, they're congruent if they're the corresponding angles. Those are corresponding. Corresponding just means it's the same angle in the transformed figure. It's the same angle. So measure of angle D is 63 degrees. Okay, suppose that square RSTV slides point for point to form quadrilateral WXYZ. Okay, so it's this rigid body slide movement. Okay, and we can visually see what the corresponding points are. S corresponds to W, R corresponds to S, because we can see what the slide is, and this is pretty simple in this case. But in general, if the transformation is more complicated, you reference the figure name. So if the square RSTV was transformed into square WXYZ, well, that tells us that R corresponds to W, S corresponds to S, T to X, or T to Y, V to Z. So you can look at the name as well. Okay, so let's see. Is WXYZ a square? Okay, well, they told us that RSTV was a square. We know that these two are going to be congruent. It's a rigid body transformation. So yes, the shape or size hasn't changed. It's just the figure has moved or rotated or reflected, right? So yes, RSTV is congruent to WXYZ. Let's make sure they're not trying to trick us here, changing the order of the letters or something. No. Okay, if RS is 1.8 centimeters, then find WX. Well, in this case, it's a square, so all the sides are congruent anyway, but these are actually corresponding anyway. RS is corresponding to WX. We can see that here, WX, RS. So WX is going to be equal to 1.8 centimeters as well. Nothing about with a rigid body transformation, which is everything we've studied in this section. Translations, flipping, rotations, the shape or the size of the figure doesn't change. The angles between sides don't change. The scale or the size hasn't changed. It's only the orientation and the location. That's why the figures are congruent after a rigid body transformation.